In the previous video, right at the end, we investigated what the result might be if we allowed 15 grams of two different reactants to react. Carrying through two different calculations resulted in differing predictions for the product's ultimate yields or outputs. And we wondered why. The answer has to do with the role of limiting reactants in a chemical reaction. A limiting reactant is a reactant that runs out first. And when it's gone, the reaction can no longer produce any more products. After a limiting reactant has run out, any remaining reactants are considered to be in excess. We saw in a previous demonstration that it only took 9.75 grams worth of sodium to react with 15 grams worth of chlorine. Any more than that 9.75 grams, and sodium starts to act in excess. In other words, there were more moles of sodium than moles of chlorine when we reacted 15 grams of sodium with 15 grams of chlorine. To be able to identify a reactant that's going to be limiting, we need to identify the thing that's present in fewer moles overall. You can watch a demonstration in a video linked in your PowerPoint slides. But what we'll say is that in the last example on the previous slide, chlorine was the limiting reactant because it was present in a smaller relative mole quantity. We can mathematically validate that assumption by calculating what I'll call a limiting reactant ratio. A limiting reactant ratio, this quantity LRR for short, is equal to the number of moles of a reactant divided by its stoichiometric coefficient. In the previous example, 15 grams worth of sodium versus 15 grams worth of chlorine had limiting reactant ratios that look as follows. 15 grams worth of sodium is equivalent to 0.652 moles. To determine that, I just divide by the molar mass of sodium, 23 grams per mole. $15 grams worth of chlorine, meanwhile, divided by its molar mass, 70.9 grams per mole, is worth 0.212 moles of chlorine. It's obvious from these calculations that 15 grams worth of sodium is worth far more sodium atoms than 15 grams worth of chlorine is worth molecules of chlorine. There are many more moles of sodium in 15 grams of it than there are moles of chlorine in 15 grams of Cl2. The limiting reactant ratio for these two quantities looks like this. The limiting reactant ratio, LRR, is the number of moles of a substance divided by the stoichiometric coefficient. In the previous example, the stoichiometric coefficient of sodium was 2. That means that the limiting reactant ratio for sodium is a number that's just a fraction, 0.326. Similarly, a limiting reactant ratio for chlorine is number of moles of it, 0.212, divided by its stoichiometric coefficient. In the previous slide's example, the stoichiometric coefficient in front of chlorine was 1. That's 0.212. Relative to how much of each of these reactants is required to make our recipe run and produce product sodium chloride, we still have chlorine present in a smaller relative amount. The smallest limiting reactant ratio identifies a substance that will run out first. And I'm going to star that substance and keep track of it. When we react 15 grams worth of sodium with 15 grams worth of chlorine, chlorine, because it's present in the smallest relative amount given by the smaller of these two limiting reactant ratios, is going to deplete first. Once chlorine runs out, there's no more of it to react and produce further products. It's like one of the ingredients in a recipe running out. After that one ingredient has run out, then we can't make any more end result. For a more practical example, suppose that we wanted to make sandwiches, and we have a reaction that converts turkey, cheese, and bread into sandwiches. 3 turkeys and 1 cheese plus 2 slices of bread makes 1 sandwich. And you go into the kitchen to make a sandwich with 18 slices of turkey at your disposal, 5 slices of cheese, and 12 slices of bread. How many sandwiches could you make according to this recipe? And how do you know that? Well, even without looking at the rest of this slide, you likely already intuitively know that you're going to run out of cheese first. And because you need 1 slice of cheese for each sandwich, the most sandwiches that you could make would be 5. That's because, relative to the recipe's requirements for turkey, for cheese, and for bread, you have the least relative amount of cheese. If we divide the amount of turkey that you have by the number required for each sandwich or reaction, you get a limiting reactant ratio of 6. If you divide the number of slices of bread that you have by the number required to make each reaction happen, you get a limiting reactant ratio that's 6. And if you divide the number of cheese slices that you have by the number required for each reaction, you get a limiting reaction ratio of 5. We expect cheese to run out first, intuitively and through a mathematical manipulation that could be applied to a chemical reaction. Cheese runs out first. It's the limiting reactant in this sandwich making reaction. Since cheese runs out first, then what we'll say is that we can always use the quantity of it to predict how much product we're going to make. All we need to focus on is the quantity of a limiting reactant, the thing that we know will run out first, for the purposes of determining how much product we can make from a given chemical reaction. We'll always use just the quantity of a limiting reactant to figure out how much product we can make. In this example, our limiting reactant is cheese. So we go from number of cheese to number of sandwich. Use a conversion factor like coefficients from our balanced reaction. 1 sandwich requires 1 slice of cheese. This is a conversion factor, just like the coefficients in a balanced chemical equation are a conversion factor. The result of this calculation gives us what we expect, or a theoretical yield for our reaction. The theoretical yield for a reaction is the amount of product that's predicted by stoichiometric calculations. Whichever of our reactants runs out first will give us a predictable stoichiometric amount or theoretical yield of a product or products. Back in our chlorine and sodium reaction example, because chlorine was present in the smaller relative amount, it had the smaller limiting reactant ratio. It alone is responsible for determining how much sodium chloride product we can make as a result of reaction. And therefore, we can ignore the contribution from sodium in excess entirely.